Well, there are hundreds of thousands of landslides that occur in the United States every year, according to Peter Lytle at the USGS. But many of these are unknown or unreported, unless they cause infrastructure damage so that our transportation is interrupted, we can't get to where we want to get to, or if they cause damage or loss of life. So how many of you have heard of the USGS program called Did You See It? A couple, good, but not enough. So the idea behind this program that the USGS has developed is, it's a website, and there it is to try to increase the information on landslides, where they occur, and what are the conditions surrounding those landslides. So this is the website, and I encourage you, if you see a landslide, hopefully from a safe distance, please go and report it and add to the information. My name is Ronda Strauch, and I'm a graduate student at the University of Washington here in civil environmental engineering. And I am working with my advisor, Dr. Erkan Istanbuloglu, looking at investigating landslides and trying to assess what it might look like in the future, both a hazard and then a risk, particularly to transportation infrastructure. So there are three key questions that I want to explore in my presentation. One is, why is the Northwest prone to landslides? What climate-related changes might alter the likelihood of landslides? And where and when might these changes occur? So to give you an idea of the number and the location of landslides, this is a map of the landslides in Washington State. This is over 46,000 landslides that are in a database managed by the Washington State Department of Natural Resources. As you can see, there's a concentration of landslides on the west side of the state and in the mountainous regions, but they're on both the climatically wet and the climatically dry side of the mountains. But even though you see this pattern here, this information is only from those documented slides. So remember the program, Did You See It? So these campaigns for gathering and documenting landslides are typically common after a severe event, severe storm, or they take place in a particular watershed of interest or in a jurisdiction. Thus, this pattern is incomplete. So later on, I'm going to be focusing on one particular jurisdiction, a little more detail, North Cascades National Park up near the Canadian border. So I just wanted to give you an idea of where that is located. So why is the Northwest landslide country? Well, first, we have lots of mountains with steep slopes, elevation ranging from 0 up to over 4,000 meters. We also have disturbances, both human-caused, such as roads or other developments, or natural, such as fires, or this is an avalanche chute. Much of the soils in the Pacific Northwest, especially in the northern section, has been worked over by glaciers over the years. So it has left behind layers of different strength in the soil and different water permeability. Also, it's left behind areas of bedrock, just sheer bedrock, which acts like pavement, and loose material moraines where our alpine glaciers are receding. For those of you who don't live here, yes, we have high precipitation, both in the form of large-scale storms and also small-scale thunderstorms. So focusing on precipitation, which is the most common trigger of landslides, what are the projections that are relevant to landslides? So theoretically, with warmer temperatures, the atmosphere can hold more moisture, so any given storm can produce more rain. And actually, people have measured increases in water vapor and downpours. So multi-model projections from the CMIP-3 models that are published in the NOAA technical report that supports the National Climate Assessment that came out recently are showing or projecting increases in annual precipitation in the Northwest, more so in Washington and later in the century. Also, the projections are showing for increases in the fall, winter, and spring, and decreases in summer. And the projections are also showing for increases in extreme precipitation, especially east of the Cascades, and where they have projecting for increases of greater than 1 inch, the number of days for greater than 1 inch of precipitation by almost 20% by 2050s. And then there's also the decrease in snowpack. So what does that have to do with landslides? Well, in watersheds that have snow, if the warming-induced changes in snowpack can influence the timing and location of landslides, because it changes the timing and the area exposed to rainfall, because the snow is no longer there, and it changes the contribution of snowpack to soil moisture. So factors affecting the stability of slopes include both inherent factors and dynamic factors. Inherent factors are static or slowly changing factors such as the slope, curvature, or the geology of an area. The dynamic factors are faster changing and often the triggering mechanisms such as rainfall or disturbance in soils. Now, in order to understand the landscape's susceptibility to landslides, we first sought to understand the inherent landslide susceptibility of the landscape. The idea being that the less stable an area, the more likely it will respond to destabilizing factors and the lower magnitude of the changes necessary to produce failure. So we chose a frequency ratio approach to identify the inherent slope stability. So this is, we based it on 6 different site characteristics: slope, curvature, aspect, elevation, lithology, and land use and land cover. We used a 30-meter digital elevation model where we calculate a frequency ratio using the formula here for each of these characteristics divided up into different bins. For example, slope, 25 to 35-degree bin. The frequency ratio represents how likely a landslide is going to occur within that characteristic and bin, given how much of that characteristic or bin is within your study area. So the greater the value of that frequency ratio, the higher the association of that characteristic and bin with landslides, and vice versa. The lower the frequency ratio, the lower its association with landslides for that characteristic and bin. So here is an example of how we apply this as a test case in North Cascades National Park. We only applied this on slopes greater than 16% and areas that were not water or wetlands. We removed areas that were less than 16% because we didn't want to develop an association between different characteristics and the depositional area of landslides. We were interested in the initiation area of landslides. And this is the theoretical threshold. So areas in this is the map of North Cascades National Park. And the colored areas are showing the areas that are greater than 16-degree slope. So you can see a large portion of the park has the potential to have landslides. And the black areas, which are less than 16%, could be impacted by those landslides, such as material going into the stream, which could then wash out the bridge, as Tom was talking about. Okay, on the right side are the results. We had frequency ratio values for the different bins of characteristics. Well, we added those up for each cell, so that the higher the value of that cell, the higher the potential for it to be unstable or associated with landslides. So the frequency ratios on the bottom and on the x-axis and on the vertical axis are the different characteristics and those different bins. So I've colored the bars that showed the particular characteristic bin that was highest associated with landslides based on an inventory that the park has of their landslides. So the results were showing that landslides are typically associated with non-glacial deposits on developed lands with slopes 16 to 25 degrees, on north to east facing slopes, on concave, curvature, and at lower elevations. Okay, so this is the map. If you take those frequency values, the ones that we added up, we had one value for each cell, and we plotted it on a map. I've zoomed in on a portion of the park so you can see more detail. So we took those frequency ratios and we categorized them into five different categories based on 20% quantiles. So the I'm only plotting here the highest three categories, the moderately susceptible, moderately high, and the high. And the existing landslides at the park is mapped. So as you can see from the graph, the areas that are showing in color with the yellow and up to red as being the most the highest inherently unstable slopes are on those valley walls. And you have more stability up in the ridges and then down in the valleys. So this empirical mapping approach provides an indication of where slopes might be inherently unstable. Thank you. But we want to expand our landslide susceptibility map to include dynamic characteristics such as rainfall by employing a mechanistic model. So the approach that we chose to use is the infinite slope stability model factor of safety, which balances the resisting forces of cohesion and friction against the driving forces of gravity. So when they are in balance, the factor of safety is 1. When the resisting forces factors are destabilizing the resisting forces or increasing the driving forces, the factor of safety is less than 1. And the slope has potential for failure. So the factor of safety equation is complex. And so I'm a graduate student in engineering department, so you didn't expect me to represent the factor of safety equation with just a couple of dogs. So factor of safety equation includes soil characteristics such as cohesion, density, and what does it call it? The factor, sorry, I am blanking on this. Friction, angle of friction. And there's a relative wetness term. It's called RW, which is essentially the ratio between the surface flow, which is like the groundwater depth, to the height of the soil. So it includes that. And Shalstab is a model that has used the infinite slope stability factor of safety model and combined it with a steady-state hydrology model to provide that relative wetness term. And that is used to adjust how much water is coming in to a particular point through how much contributing area is coming down to that particular cell. So this is an output of that particular model, Shalstab, which shows you some of the soil layers in that same zoomed-in area of the park. And that darker blue shows you areas where the soils are saturated. So this is if a rainstorm came into this area. This is the area where you'd expect higher saturation and more probability of unstable slopes. The model also produces a factor of safety. Remember that greater than 1 that we're looking for. So if it's less than 1, that's unstable. So that would be shown in red. And in this case, to drive the model, I use the average November rainfall and a root cohesion factor that's for Douglas fir forest being mature. So if this entire park was covered in Douglas fir forest and had an average soil depth of 1 meter, it looks like it would be completely stable in November. But what if we increase that rainfall and we also decrease that root cohesion, so maybe the area had some fires? This is how it would change, and all the red is showing areas where you potentially have unstable conditions. But this shows a lot more red than that inherent stability map that I had showed you earlier. So this approach, this mechanistic approach, is still missing some of the geology and some of the local land cover characteristics that you get from that empirical approach. So our next steps are to incorporate the future climate change into that relative wetness factor of the infinite slope model. So this is just showing you percent change in climate, percent change in precipitation by the 2040s in North Cascades National Park. And that same little highlighted area, it's actually a little bit low, is that blue area there and here. And what I'm trying to show here is the percent change, even with statistically downscaled models, can still show some variability spatially. So in November, it may have a higher rainfall in the future than in the past, but also in summer at the same location, but not over in these areas, even though the general projections for the summer is drier conditions. So you really need to look at a finer scale. So what our next step is to integrate these two models so that we can capture some of the geologic site characteristics as well as the physically based model into an integrated slope stability model. And then this could be used for the risk assessment for infrastructure, for example, so we get a better idea of where on the landscape and when our landslides will be at the highest potential. So we want to make this to be a probability model. So in summary, because we're running out of time, the Pacific Northwest represents a natural laboratory for studying landslides. Landslides depend on both inherent and dynamic factors. Increased precipitation may shift dynamic drivers to increasing instability, varying both space and time. An integrated model will capture the geologic, and the hydroclimatic factors. So it's a more complex model, but we expect to be a more accurate model. And then last point I want to make is we need more information on landslides, locations, and triggers. So there's that website again. If you see it, please report it. And I want to acknowledge funding for the Northwest Climate Science Center and the National Science Foundation, partnership with the National Park Service, and data that comes from the Climate Impacts Group. Thank you. Questions?
So how important are the changes in the short-term precipitation, let's say over an hour, versus that over a long period like a month? Because, I mean, the
Yes, good question.
may be different for these two different types of precipitation.
And for different types of landslides. So one landslide, but he was talking about the difference between short-term intense precipitation versus more longer duration, maybe less intense precipitation. And I think it still depends on site-specific characteristics of where you're looking at. I think you're going to have both, especially if you had them both in combination. If you had that sequence of events, sequence of weeks with high precipitation, and then you had a downpour, so the soil's already relatively saturated, and then you added in on top of that, you could push it past that threshold. But if it's also saturated and it's still stable, then you're adding all that water on there, and instead it can't fill the soil, it's just going to run off. So then you've got dealing with flooding and other issues, not the landslide. So this really depends on where you're looking at. So they both need to be looked at, and the different types of landslides, whether it's a deep-seated landslide or shallow surface landslide. That'll make a difference as well. The longer duration one might be should be much more important for those deep-seated ones, because it's getting that time to really soak in and go down deep to a layer that might slide. Other questions? Oh. Go ahead. It's very good. It's a very good point. Yeah. It's a good question. He's asking me about, I showed some of the examples in relatively undeveloped areas, natural forests, natural conditions. Well, what about in more the urban areas or even rural areas where you've got more development going on? And that's why that inherent stability, those different site characteristics is so critical, because that had that land cover and land use variable in it, which is why that developed bar was so high. There's very little development in North Cascades National Park, and yet that was the one that popped out the highest as being associated with landslides. So that's why you have to do both. You need that empirically based, that site characteristic specific one, and then you need that dynamic one when you're bringing in the actual triggers and the drivers. You put them together, and then you get a better result. Another question? The run out. Yeah. Okay, so I think if I make sure I do this correctly, I think you're mostly focusing on how do you assess the run out from the lands. I mean, I'm talking more about the initiation zone, but the run out, as we saw with OSO, is very important. And we haven't got to that yet, but we will get to that. There are various ways of predicting the run out of landslides, and also depending on the landslide. And so we want to explore those different ones. And also, what did they learn from OSO that might change the methodology for that predicting that run out? And then, once we have that prediction, we can apply it to the existing landslides we have or the landslide cells that are the most at risk for failure to give us a footprint of where this might go and then what is in the way that might get impacted.
All right, thanks, Rhonda.
Okay, thank you.
So thanks, Rhonda, and thanks to all of our speakers today.